Great, thank you so much for introducing us. Hi, everyone. We are Beat the Heat, California Wildfire Prediction. We're composed of 7 group members: Kaylee, David, Saulo, Sergio, Tyler, David or Makoto, myself, and Leor. All right, well, let's just jump straight into it. So just to give you some structure to our talk, we're going to give you a quick introduction to the field that we're working in. Then we're going to talk about some related work, what's been done in the field before us. Then we're going to move on to design, give you a high-level perspective of what we did, talk about some algorithms that we used. And then we're going to give you some implementation details before we show you our results and analyze them, and then wrap up. All right, so introduction. So our topic is on wildfires. Our goal is to do whatever we can to combat them. And so I don't think I really need to convince anybody in this room, I don't think I need to convince anybody in this Zoom that wildfires are a detrimental issue that just catastrophic to almost any region that's affected by it. If I do need to convince you, there's a nice little diagram right here. Turn on my laser. Just from the years 2019 and 2020 from the California Fire Incidence Record, this is just the damage that's happened in 2 years in California. Lives lost, wildlife, millions of acres burned. It's just a horrible issue. So, as computer scientists, we can't do a whole lot. We're not as maybe useful as on the front lines, but we can do what we can from the back end. So with that said, we set out with a goal to try and predict wildfires, since there's a lot of prediction technology, modeling, and stuff like that. But what does that mean on a more technical level? So on a technical level, what we set out to do was to find some features that were influential to wildfires from satellite images. So features could be things like factors like the temperature of the surface of the earth. It could be things like how dense the forest is in a certain region, how green it is, things like that. And if we can link that to what causes a fire, then we can really train some of these models to make highly accurate predictions. And that's exactly our goal. So pretty much what we do is we give a number of conditions to our models, and then we also we look at past fire records and we say, oh, these conditions on this specific day, they did lead to a fire. So we're going to classify that as fire conditions, vice versa for no fire. We'll talk more about that in a minute. And just a quick note, some gaps in the current research in the field, but that there was a lack of emphasis on California being a region of interest. So since it's so close to home, we decided to might as well just use our data set have California be our data set. All right, so onto related work. I'm just going to talk about the data sets really quickly. And this is some key terms that are going to come up quite a bit in our talk. So these are actually the features that we selected, but it also came up a number of times in other papers, as you can see here. So this top section on the left here is satellite data, whereas the bottom left section is like in a table format or an Excel file, CSV specifically. So the first feature that we selected, thermal anomaly, is a fire detector of sorts. Basically, there's an instrument on a satellite that has an infrared sensor. It looks at reflectance levels on the surface of the Earth to determine with some variable confidence that whether or not there's a fire. Land surface temperature is pretty self-explanatory. Temperature of the surface of the Earth. Normalized difference vegetative index, it's a mouthful, which is basically, you can see the word vegetation in here. It just has to do with the crop health, kind of like the greenness of the crops. And you can see on the right here, we talk about that, or it's shown on the right. Burn area is kind of similar to thermal anomaly in that it looks for fires and then records them. So it's kind of like a fire record of sorts, but it also comes in an image file. And they come with data like the specific day of the year that there was a fire in a certain area with a variable level of confidence. And so we use that a little bit later. And then we also have this fire record down here. As we mentioned, if we can look at past fire records, we can tell our data, our models, which data it should be classified under. And this is government data, so very reliable. So moving on to model related work. So there's a lot of information here, but I mainly just want you to look at the center column right here with the models. And you can see that neural networks and support vector machines came up quite a bit with fairly high accuracy. So it played a big role in our choice of models. All right, now on to Kaylee with design.
Beat the Heat is composed of 3 major parts. First component is preparation, which includes the step of data collection, analysis, and pre-processing. Second component is model building, which includes the step of training, validation, and testing. And the last component is quality measurement, where the model will be evaluating and deployed. And the detail of each step will be explained in the next slide. First, we collect the data products of NDVI, LST, TA, and BA from NASA Earth data, and California Fire Incident Report from CAL FIRE. Then we apply the data cleaning, clipping, extraction, interpolation, and iteration. These techniques will be explained more later in implementation. In model building, we first split the data into two subsets for training and testing, then feed the data into training and look back between validation and training until the model is validated, then test the data with the test data set and output the prediction result. We're using the top 5 binary classification models, which are neural networks, support vector machine, k-nearest neighbor, Gaussian naive-Bayes, and logistic regression. The reason we use binary classifier because we only have 2 values in our class column, which are either fire or no fire. The tool we're using mostly Python libraries, and Tyler will continue with neural network.
All right, thank you, Kaylee. So let's talk about neural networks. What is a neural network? The simple answer is layers of neurons that are connected to one another, and you can think of these neurons as simply an object that holds a number. The connections between these neurons have weights, which are values that are used to modify the values that get sent on to the next input layer. So they learn by minimizing what's called a cost function, which you can think of as the amount the model guesses incorrectly. So this can be done using a process called gradient descent. And to put this idea into a simple example, we can think of the game of hot or cold. So each time you take a step in a given direction, you're told whether or not you're closer or farther to the goal, and you can correct your movements to eventually guide yourself to it. And generally speaking, this is what's happening behind the scenes in a neural network model when they're training and doing weight modifications. So the model style that we decided to go with was a feed-forward network style, and this makes use of backpropagation as well. So the figure shown here is a general example of this type of network flow. So feed-forward refers to a non-cyclical style of neural network in which the data is passed through multiple layers of neurons strictly from input to its output. Backpropagation is used to help identify which of these neurons contribute to the errors in the output from the network, and when those errors are encountered, the weights between the connections are then modified in order to guide the network to a more accurate result. So data is basically fed through the network and a linear combination of neurons and weights is calculated. Each neuron's output is passed through an activation function and it's compared against a threshold, which will determine if its value becomes part of the input for the next layer or not. And this process is repeated between each of the sets of layers. Support vector machine. So support vector machine is a perfect fit for what we're trying to do because we're operating on a basis of fire or no fire, which is inherently a classification problem, yes or no. So the main goal for the model support vector machine is that it's trying to find the optimal hyperplane, which is just a decision boundary of the largest margin between these classes. And the points closest to that optimal hyperplane are called support vectors, and they serve as training margins, training points for the maximum margin. And when the data doesn't have a linear relationship, SVM basically scales quite nicely due to kernels and kernel tricks. And we can achieve a nonlinear plane between our classes by mapping data from a single dimension to a higher dimension. And that's what the kernel function is doing. And the kernel trick basically is using inner products to make higher dimension calculations faster and more efficient. And there's a couple different kernel options that you can go with for something like this. There's polynomial, Gaussian, sigmoid, and hyperbolic tangent. And next, Kaylee will talk about the other models that we tested.
K-nearest neighbor is a non-parametric algorithm, meaning there's no assumption for the underlying data distribution. In other words, the model structure determined from the data set. K is the number of nearest neighbors and are the core deciding factor. KNN has 3 basic steps, which is calculate the distance, find the closest neighbors, and vote for labels. Next slide. Gaussian naive-Bayes is a variant of naive-Bayes, and one assumption of this model is that the feature have to follow a normal distribution. The model can be fit by simply finding the mean and the standard deviation of the points within its label. Next slide, please. Logistic regression is the name of the function used at the core of the method. The logistic function, was also called the sigmoid function, is an S-shaped curve that can take any real value and map it into the value between 0 and 1, but never exactly at those limits. Next slide, please. In quality measurement, we will take the prediction output from model building and evaluate them using confusion metric and classification report. So some terminology included in the report are true positive, which means correctly predicted there is a fire. True negative is correctly predicted there is no fire. For positive is incorrectly predicted there is a fire, and for negative mean incorrectly predicted there is no fire. Next, Makoto will continue with implementation.
Great, now on to the nitty-gritty details. All right, so for data preparation, what I'm gonna do is explain to you how we prepared our NDVI, our vegetative data set, because for thermal anomaly and LST, it's the exact same process. So I'm just gonna start with, oops, sorry about that. All right, so as you can see, the first step is data cleaning. So data cleaning is to remove pixels that were damaged or just a low quality due to cloud cover, instrumentation malfunction, etc. You can see here that this is actually a real image from the data set that we use, the visualization. And you can see there's missing pixels on here. So we just literally remove those and then use the rest of the data set if it wasn't all corrupted. So next we did this technique, which is called clipping, and we clipped it by the burn area. So if you remember, the burn area is this data set that has past fires embedded in it. And so pretty much what we did is we wanted to clip out these areas. So I'm just going to explain clipping really quickly. So clipping in terms of image files is, you can think of it as if you overlay two different images, you're going to look at the regions that overlap, kind of like these red regions right here. And then you're going to cut those out of the original image and then set it aside, kind of like a cookie cutter. So you can think of it this way. If these numbers right here are NDVI values ranging from 0 to 1, this is the burned area region in red. We literally just grab that, average all the burned area, all the clip to burn area region values, and then store it with the date. So we grab all these for each day, and that's a row. So the reason we do this is so that if we flag an entire day's worth of conditions as fire conditions, we're not going to be flooding our model with all this data that has nothing to do with fires, because if it did, it would be on fire within the same month, which is the reason why we clip by this. So you may be thinking, so that's essentially what we did for all three of the data sets. Now I'm going to explain a separate path that we took. So one thing that came up was maybe if we're, using such a big region and classifying it as one area, there might be some errors that compounded or through each step. So what we decided to do was to treat it instead as 58 regions in a separate data set. We call this the data by county. So we actually use the exact same technique of clipping. And so we just enter some shape files, and then essentially if this backdrop is also the NDVI data, we're going to say get Fresno here. And we're just going to clip out the values that are within the Fresno county boundaries. And then we're going to average the values of each county's region and store it with the county ID and the date. It should be noted that for this data set by county, we did not do the masking by burn area or clipping by burn area because we ran into some issues, and it's somewhat error prone, the data clipping. All right, so now that I've shown you how I got the NDVI, or how we got the NDVI for both the county and state level data sets, as I mentioned, it's the same for LST and TA. Now I'm going to show you how I got this last column here, the fire column, how we got the fire column. So we got this directly from the fire record, which is government data. And this data kind of comes in the form of fires, the dates that it was burning, and the counties that were affected. So if I made a quick little visualization here. Say there's a fire in LA County, San Bernardino, and Redding area up here. For the state level data set, what we would do is if there were at least even one fire in the region, we would say that the whole region is on fire, and we would set this column over here on the right to fire. And then, we would label all the corresponding conditions for that day as fire as well. So, of course, we would clip by the burn area, and then that would reduce error by a lot. But on the county level data set, what we did is, since our data is already categorized by county and by date, we can just directly link it up to the fire record, which also comes with county specificity. And then we can just say like, oh, just San Bernardino's on county, but San Diego isn't. All right, so for model implementation, the data was split 80% for training and 20% for testing. Several different combinations of neurons and layers were used for the neural network. Also, several different combinations of parameters were used for each model until we reached the current accuracy score that we got. All models were used from scikit-learn, and if you need more information, it'll be available in the sources below. All right, now on to Tyler.
All right, so let's talk about our results here. As you can see, out of all the models tested, the support vector machine produced the highest testing accuracy with that initial data set that we had, coming up at 93%. And in the top right, we have the confusion matrix for the support vector machine results. And this showed us that it was getting a low amount of false positives and false negatives, which is what we wanted to see and why it was producing such a good accuracy. And the neural network struggled to get accuracy above 81%, and I believe that's partially due to the amount of data that it was trained on in this first data set. Neural networks typically work better when they're trained on large amounts of data, and it gives them more to work with, making those connections, modifying those weights. So before we move on, make note of the class count in the bottom left there and how the amount of no fire values compares to the amount of fire values. Here the ratio is like 1.5 to 1. And then with the data set where we added county, it increased the overall size of the data set significantly. So it seemed to produce great results at first, but we had to look further into the predictions, and we noticed that the model was heavily overfitting the data, which is detrimental to producing a model that can predict accurately on a new set of data. That's what overfitting means. Basically, the model is trained too well on one specific type of data. And so compare the class count here to the confusion matrix of the previous one. And you can see this data set has significantly more no fire values, now a ratio of 30 to 1, which is an extreme imbalance, and that's not what we wanted. So the only reason for these high prediction accuracies from this set was due to the fact that the model was basically trained to predict no fires majority of the time, and then was tested on a data set that contained mostly no fire values as well. So this is a prime example of why we want to use these classification metrics, like confusion matrices, class counts, classification reports, because without them, we may never realize that the model was doing that overfitting. So to conclude here, although other work has been done before on wildfire prediction, there wasn't much that had been done specifically for California, which prompted us to take action. And the approaches taken provided promising results for the field of machine learning and remote sensing. The models used give highly accurate predictions of regions that are likely to be on fire, the most noticeable being that 93% in the first data set, since those accuracy results were better. And for future work, increasing the accuracy of the fire indicator by using burn area instead of the fire incident record. So compared to the fire record, the burn area is more precise, and it labels fires down to daily frequency and a 500-meter grid pixels. And moreover, fixing the imbalanced county data set is another option by reducing the ratio of the fire to no fire values. And this can be done either by locating a specific forest or county which fires occur more frequently in, or by resampling the current data set and pulling up values to make it more balanced. Lastly, we have the option of finding or creating another data set as well that includes different fire conditions and factors to see if that changes results at all. We'd like to give a few acknowledgements, first and foremost to Dr. Jiang, our senior design professor. She helped us a lot in getting to where we are with this project. We'd like to thank CSUN Library for all of its resources, NASA for its satellite images, the California Fire Incident Report, and the Python libraries that we used. And then here are our references. And we'd like to thank you all for watching our presentation. If you'd like, we have our website down there and you can visit that. We have some demo videos and a few interactive tools as well there with a little more information. And if you have any questions, let us know.
Good job. Good job.
Yeah, good presentation. Enjoyed it. It was very much centered on artificial intelligence and data processing. Can you give us a little bit of an idea of the mix between the software development aspects, how you utilize some of the tools, as opposed to just processing the data?
Sure, I can take this one. Yeah, so we use GitHub quite frequently in this, constantly handing back code back and forth to each other. We also use Jira, as a lot of the other groups have mentioned. Let's see, what else do we use? Discord a lot, handing code over a lot there, but mostly GitHub for that. Yeah, and lots of organization. I think we mostly used, Kaylee and I were project managers, with Kaylee being the technical lead, but we used a lot of local notes and stuff like that to print out little reports and kind of get everyone up to this, keep everyone on the same page after our meetings.
Okay, thank you.
I had a follow-up to that on the technologies used. So you mentioned Python scripts and, with machine learning, as you noted, there's various algorithms that you use to help figure out, discover what's in the data and then, train it so that you can put new data through it. So what process did you use to actually work with the data? You gave us the results, but did you customize Python scripts? Where was the data? Walk us through that technical process to get to the results you described.
I can answer that question. So most of the model we use is implemented in scikit-learn, and the way we use it is depend on the data site, and it depend on so we have binary classification. So we have to look for the behavior of each model on the data, and then we changing number of parameter. We change different number of parameters, and we changed different number of the size of the data in order to make increase the accuracy.
Great, thank you.
Thank you.
For all the questions, and just want to share with all of you, and our department started offering a minor and in data science, as you can see, and I was student and really like to work with big data and to work with data like from different domain, different areas, right? And so if you're a junior or like a sophomore level, you can start thinking about and taking that minor and along with your degree. Okay, but great job, and be the head team.